PreAP, PreCalculus, Notes 3.6, Graphs of Polynomial Functions. We're going to be adding a little bit of new stuff in this section, but then it's going to be a ton of review for this chapter. What we're going to be adding that's new, well, that's happening right here, right off the bat. Complete the following table. Identify the end behavior rules for any odd or even degree of polynomial function based on the degree of the function and the leading coefficient. So, in essence, a function can be odd or it can be even. The leading coefficient for an odd function can be positive or it can be negative. So we can have a function that's odd degree with leading coefficient that's positive, or odd degree leading coefficient's negative. We can have an even degree function whose leading coefficient is positive or negative. Now the left end behavior, just want to remind you, it's asking this question. What's the limit of the function as x approaches negative infinity? Now it's the same question that we're asking for each of these scenarios. As we go left forever, what's happening to y? Is it going up? Is it going down? The right end behavior of the question every time is, what's the limit of the function as x approaches positive infinity? In other words, as you go right forever, what's happening to y? Is it going up? Is it going down? Is it approaching a number? Does it not exist as you go right forever? So we need to examine these four scenarios. Scenario one. Now, I don't recommend blindly memorizing this. I do not have this memorized, and I've been teaching this for a few years now. What I do is I try to think, do I know an odd degree function whose leading coefficient is positive? And I sure do. The easiest one that I can think of is y equals x, which I believe we all know looks like this. Has a y-intercept of 0, which is not relevant for what we're talking about right now. It has a slope of 1, which is relevant. So what happens to this odd function with leading coefficient that's positive? Leading coefficient will be 1 in this case. As it goes left forever, it's going down. So the end behavior for this is y is approaching negative infinity. What's happening to this function as you go right forever? Well, it sure looks like it's going up. So the end behavior on the right, the limit of f of x as x approaches infinity, is positive infinity. Second example. Can I think of a function has an odd degree, leading coefficient's negative? I sure can. Y equals negative x. I know what that function looks like. It looks like this. The end behaviors here are the opposite of these. As this goes left, it goes up. Therefore, as the limit of f of x as x approaches negative infinity is positive infinity. As we go to the right, it goes down. As x approaches infinity, y is approaching negative infinity. Number 3, what happens if we have an even degree and leading coefficient's positive? Well, I can think of an easy example of that my brain always has chambered. It's a parabola. Both of those end behaviors as you go left or right are going up. So the left and right end behavior are going to infinity. How about an even degree with leading coefficients negative? Y equals negative x. That's a parabola that opens down. Both the end behaviors are the same. They are both going to negative infinity. To sum up, if it's odd degree, the end behaviors are opposite of each other. If it's even degree, the end behaviors are the same as each other. If it's even degree and the leading coefficient's positive, it opens up, or I should say the end behavior is infinity. If it's even degree and the leading coefficient's negative, end behaviors are going down. If it's odd with a positive leading coefficient, it rises to the left, it falls to the left and rises to the right. If its degree is odd and a negative leading coefficient, it rises to the left and falls to the right. All right, let's check out completing the table for the time being. Let's ignore this. I meant to have that marked out. Shame on me. Complete the table below for each graphed function. So we have a function. It's not named, unfortunately. Let's just say this is function f for giggles here, and let's say this is function g. So what are the zeros and their multiplicities? Now, we've studied this a lot in this chapter. Hopefully you can clearly see this is a 0 at -3, and this is a 0 here at 1. What's the multiplicity at -3? Well, at -3, it's crossing the x-axis, so it's an odd multiplicity. It's changing concavity at -3, so it's an odd multiplicity that's at least 3. At x equals 1, it is crossing the x-axis, so it's odd. It does not change concavity, so that's equal to 1. So what type of function is this? What's the degree of the function? The directions say degree and type. So degree we can nail down with some uncertainty. Type we can also nail down with some uncertainty. 1 plus 3 is 4. Since this is odd and it's at least 3, it's going to be 3, 5, 7, 9. If you add two odd numbers, you're always going to get an even number. So we would say this is even degree. And it's even degree of at least 4. So this is at least quartic. Determine if the lead coefficient of the equation is positive or negative and justify your conclusion. Well, we know this function is even degree, so we've established that right here, which means the end behaviors are the same, and the picture clearly shows that. Since this is falling to the left and the right, the lead coefficient is going to be positive. So formally, function is even degree with both end behaviors falling. Therefore, the lead coefficient is negative. Make sure I answered the question. Determine if lead coefficient is positive or negative. Did it justify your conclusion? Write the possible equation for this function. Now, the possible equation for this function is f of x equals, we have our zeros that become factors using the factor theorem. Now, the lead coefficient, some number a, we are saying that that is negative. So to emphasize that, we're going to say negative a. G of x, this next function, we have a 0 at -2. It's crossing the x-axis, so it has an odd multiplicity, and it doesn't change concavity, so it is equal to 1. At 1, we have another 0. It is even multiplicity because it's tangent. So we know it's at least 2, but we don't know for certain what it is. What is the degree of this function? Well, it's definitely odd because 1 plus an even number is going to be odd. One plus 2 is 3, so it's an odd degree that's at least 3. What type of function would this be? This would be at least cubic. Now keep in mind, I'm combining it's at least cubic with the fact that it's odd. So it couldn't be quartic, it could be quintic. So our conclusion for this last question, which is determine if leading coefficient is positive or negative. Function is odd and rises to the left and falls to the right. So I'm just stating the observation. It's odd, rises to the left, it falls to the right. If you think about our parent graphs, that is the same resemblance as y equals negative x. Therefore, the lead coefficient is negative. A function for this, g of x, using the factor theorem, we have factors of x plus 2 and x minus 1. You know, I don't think I emphasized on this previous one. this x plus 3, I said it was to the third. I don't actually know it's to the third. The directions here say write a possible equation. I know this is an odd degree, and I know it's at least 3. This could be a 5 or a 7 or a 9. I don't know. When we write our answers, let's write the smallest number that it could be here. I apologize for not emphasizing that on the previous problem. So this one here, we got factors of x plus 2 and x minus 1. X minus 2 has an x equals negative 2 is a 0. Therefore, x plus 2 has an odd multiplicity of 1. We've already established. I threw some therefores in there in that last sentence that don't make any sense. Odd multiplicity is 1, so this is 1. X equals 1, which is the factor of x minus 1, has an even multiplicity of at least 2, so let's say that this is 2. Leading coefficient we said is negative, so we'll say it's a negative a. All right, let's call this next one h and this one k. And let's once again ignore this. All right, what are the zeros of this function? Function h. We got one here at negative 3. It's going to be odd degree because it changes concavity and crosses the x-axis. We have one here at 1 and one here at 2, both odd degree of multiplicity 1 because they do not change concavity. So we got x equals negative 3, odd at least 3. X equals 1, x equals 2, both odd degree of 1. 3 plus 1 is 5. So this is at least quintic. The degree is odd degree of at least 5. Since this is an odd function and it rises to the left and falls to the right, the leading coefficient is negative. So our function h, we have a negative lead coefficient, and our factors for this are x plus 3, which has an odd multiplicity of at least 3, x minus 1 has an odd multiplicity of 1, and x minus 2 has an odd multiplicity of 1 as well. Alrighty. K. K has zeros at negative 2 and 1. At negative 2, it's odd multiplicity that's at least 3 because it changes concavity. 1 is an even multiplicity because it's tangent. So we have a 0 at negative 2, 0 at positive 1. Excuse me. At 2, it is odd multiplicity of at least 3. At 1, it's even multiplicity of at least 2. So if we take 3 plus 2, we're going to get at least quintic again. This is an odd degree polynomial of at least 5. It's odd and it falls to the left and rises to the right. Therefore, the lead coefficient is positive. Oops. As far as our function goes for this, This is function k. We're saying the lead coefficient's positive, so I'm just going to put an a here. One of our factors is x plus 2. It has an odd multiplicity. Another factor for this is x minus 1, and it has an even multiplicity. It's at least 2 and at least 3. Let me erase these things down here. Sorry. I meant to do this ahead of time, and I did not do it ahead of time. All right, the table below shows values of a quintic polynomial. It's degree 5. The zeros in the table are the only zeros of the function. So there are no hidden zeros. Answer the questions that follow. Now, when I look at this, I immediately identify those zeros. So I'm going to move this 5 so I don't confuse it with what's happening here. Here's a 0. Here's a 0. Now, is there a way for me to determine right now if these are the only zeros, whether these are even or odd? Well, on the left of negative 3, on the left of negative 3, the y values are negative. On the right of negative 3, they're positive. So here we are crossing the x-axis. So this is an odd multiplicity. Here at 1, it's positive on the left and positive on the right. This is an even multiplicity. So at this point, since it's quintic, our possibilities are this is odd and it's 1, and that makes this 4. Or this odd could be 3 and this even could be 2. Both of those add up to 5. And at this point, I don't think there's a way for us to figure out what that is. A, identify the left and right end behaviors. To do this, we are going to look as far left as we can and as far right as we can. If you look as we go to the left, these numbers start to get real big negative pretty fast. So it looks like as we're going left, it's approaching negative infinity. So the limit of f of x as x approaches negative infinity, it appears to be approaching negative infinity. The limit of f of x as x approaches positive infinity. As our x values get bigger to the right, these y values start to get real big. So it looks like to me it could be going to positive infinity. Based on the end behavior, what must be true about the degree of the function and about the sign of the leading coefficient of the equation? Now, it doesn't say anything about the directions. It says based on the end behavior alone. Based on the end behavior, these are going in opposite directions. Therefore, this has to be an odd function. Since the graph is falling to the left and rising to the right, the lead coefficient has to be positive. The end behaviors are opposite of each other, therefore the degree is odd. The graph falls to the left and rises to the right, therefore the lead coefficient is positive. Next question. Identify the zeros and multiplicities of the zeros of f of x. Justify your answer. Well, as previously stated, f of x equals 0 at x equals negative 3 and x equals 1. I mean, the table clearly shows that. There's no dispute. Therefore, f of x has zeros at x equals negative 3 and x equals 1. That's what it means to have a 0. F of x changes signs at x equals negative 3. Therefore, f of x has a crossing 0 at x equals negative 3 with an odd multiplicity. That odd multiplicity could be a 1, could be a 3. f of x doesn't change signs at x equals 1. Therefore, f of x has a tangent at x equals 0 with an even multiplicity. We can't say for certain what these multiplicities are. We could give possible combinations of those. That's the best we could do. Next page. Let me hide this stuff again. Once again, I'm sorry. This was supposed to be done before we started the video, and I didn't do it before I started the video. I want to go back and point something out on this previous one. Emphasize something. When we get to this statement here and say f of x has a crossing 0 at x equals -3 with odd multiplicity, there are two things that we are stating here. We're saying that it's a crossing 0 and has an odd multiplicity. This next one, we are saying it's a tangent 0 with even multiplicity. This word crossing and this word tangent, they are important. It's crossing because it's changing signs. It's tangent because it doesn't change signs. Originally, when I wrote this, I wrote as two different sentences. F of x has a f of x crosses the x-axis at x equals 0. And then I said that 0 has an odd multiplicity. Well, I combined this into one sentence by just making crossing an adjective, tangent an adjective. Those words are important. Similar problem. Table below shows the function values of the polynomial. The zeros in the table are the only zeros. That's important. Only zeros that were going to happen are in the table. No zeros have a multiplicity greater than 2. Well, that sounds like that's pretty important. So the most multiplicity you could have is 2. Answer the following questions. Well, let's identify what some of these zeros are. I would do this before I tried to answer any question. So we have 1, 2, 3 zeros, 3 distinct, unique zeros. This one here is going to be even. And I know that because the y values aren't changing at the x-intercept. This one here is going to be odd because the y values are changing signs. When I say odd, I mean odd multiplicity. This last one is also an odd multiplicity. Now, these odd multiplicities have to be 1 because no multiplicities are greater than 2. So I can say for sure these are each 1. Now, are we told what type of function this is? We are not. If this is an even multiplicity and it can't be greater than 2, then that means it has to be 2. So this function is 2, 3, 4. It's a quartic function. We know that for certain, based on all the information that we're given in the directions and the table. Identify the left and right end behaviors of a function g. The limit of g of x as x approaches negative infinity. That's the question on the left without looking at the table. What's the limit of g of x as x approaches positive infinity? That's the question about the end behavior on the right without looking at the table. Well, let's look at the table. As we go left forever, as the x values get big or negative, what's happening to the y values? They are getting big or positive. As we go left, we are going up. What's happening to the end behavior as we go right? Also going up. So both end behaviors are going to infinity. Based upon the end behavior, so we're just looking at end behavior only, what must be true about the degree of the function? Well, both end behaviors are rising. Therefore, the degree of f of x is even. And since they're both rising, then it has a positive lead coefficient. I didn't finish reading the question. What must be true about the degree and about the sign of the leading coefficient? Give a reason. So here's our reason. Both end behaviors rise. And our two conclusions are the degree of g of x is even, and there's a leading coefficient that's positive. Identify the zeros and multiplicities of each zero of g of x. Justify your answer. We talked about that at the beginning. G of x equals 0 at x equals -3, -1, and 2. Table clearly shows that. We are drawing no conclusions. Conclusion we can draw from that is that g of x has zeros at x equals -3, -1, and 2. G of x changes signs at x equals -1 and x equals 2, and no zeros have a multiplicity greater than 2. That's what the directions say. Therefore, g of x has a crossing 0 at x equals -1 and x equals 2, with each having an odd multiplicity of 1. Once again, this word crossing is important. It needs to be included in your answer. G of x doesn't change signs at x equals -3, and no zero has a multiplicity greater than 2. Therefore, g of x has a tangent 0 at x equals -3 with an even multiplicity of 2. Right, that's going to conclude this part of the notes. We got more to do, but we'll cut this off right here, and we will get to the next one.